Okay, so welcome everybody to this colloquium. We have a very special speaker today, which is Professor Anders Johansen from Copenhagen University. So he did his PhD in 2007 in Heidelberg, working with Hubert Klar at this point. Yeah, it is on. About disk hydrodynamics, instabilities. And then he moved on to Leiden as a postdoc and soon won a Veni fellowship, which is quite prestigious. But just as he did that and worked on some AGN disk stuff, he got actually an offer for a permanent position. So he moved on to Lund University in Sweden for a while, for 10 years. And then in 2020, he took the chance to change to the University of Copenhagen at the ÖAW-Institut. And he's a well-known scientist in the regions of, say, dust, hydrodynamics, coagulation, dust processes, planet formation in particular, hydrodynamics, and recently also chemistry, and that's why we invited him now. And there's also, he brought a student, so this is Marie-Louise Steinmeier. If you want to stand up, please. And she will be here. She will be here doing a small scale project in, I think, in March. Yeah. And so we are also having already started discussing about what she can do. Now, Anders is kind of hard to avoid at conferences because he will always give these prestigious review talks because in the end, you know, he's doing what everybody wants to know, and that is how do you go from small particles, pebbles, to planets. So the real dynamical ideas of how planet formation actually works. And he's well known for this, for two things in particular I want to mention. So this is the streaming instability. I'm sure we will learn something about that today, and about pebble accretion. Okay, with no further delay. Now it should work.
Okay, and I've unmuted myself. So thank you very much for this introduction. It's a really great pleasure to be here today. And particularly, I want to talk today about the accretion of rocky planets and also the outgassing of their first atmospheres. But to get to the rocky planets, I'll sort of go through all the stages of planet formation first, and particularly the theory of pebble accretion and how we worked on forming planets by pebble accretion in my group for the last decade or so. I want to show the progress that we have made on this. All right, but let's start with a little bit of motivation. Of course, we want to find habitable planets outside of the Earth at some point. And if we look at sort of the planets that are known now to orbit around other stars, there are quite many of them. This is from the Kepler satellite data. And it shows here the orbital period in days and the radius of the planet in Earth radii 1, 4, 10 Earth radii. There are all these planets basically that are many of them and very good statistics for now. We actually know more than 5,000 exoplanets. And of course, the discovery of the first exoplanets was rewarded the Nobel Prize in Physics in 2019. But if you look at this plot here a little bit more critically, you will notice that the period in days here is very short. All these planets are orbiting sort of within the orbit of Mercury, and all of them are very hot and probably not particularly habitable. If you go out and study planets in the habitable zone instead, then there are not so many planets known to orbit around other stars. This is a plot I took from Kosakowski et al. 2023, based on the Kamenis search for planets around nearby stars. And it shows all the small planets we know here as a function of the insolation in terms of the Earth's insolation. So one is the amount of radiation that the Earth receives from the sun, and 1.5 times is more, and 0.5 times is only half that. And you don't see it so well on the screen now here, but there's a habitable zone marked here between sort of 1.5 and 0.3 or something, where you could reasonably have liquid water at the surface. And then we see not so many planets left, like a couple of handfuls here. Now, one of the famous ones here, we can take a few famous. There's a TRAPPIST-1 system. Notice the stellar temperature here, very, very cold star. very orbiting close to the star, but still in the habitable zone. You see there's the Trappist-1 system here. You see Proxima Centauri here. The nearest star to our own sun has a small planet, Earth-like planet in the habitable zone around it. So there are habitable planets out there. We don't know so many of them yet, but we will of course know more and more of them. And it's sort of a holy grail now of science, I would say, to find out how do such small, potentially life-bearing planets form, and also where do they get their volatiles from, what kind of atmospheres do they outgas, and in the end we want to understand if life is common on other planets also, or if it's only arose on the Earth around the sun. Okay. So the planet formation process can basically be summarized as a growth of dust to larger and larger bodies. This takes place in protoplanetary disks around young stars, and it takes us from sort of micrometer-sized dust like this interplanetary dust particle, this IDP here, and all the way to fully fledged planets that are 13 orders of magnitude larger than that. So there's a lot of dust coming together to form one Earth-like planet. And we can sort of divide the planet formation process into a number of stages. So the first one is all the dust and ice particles stick together to form something like millimeter-sized pebbles, as we see here. These are actually made in a lab in Braunschweig. These pebbles here, the grid is a millimeter in size, and they are made from aggregates of micrometer-sized dust grains. But then a number of questions arise now, and I'm sort of interested in three fundamental questions of planet formation. How do the pebbles come together to form kilometer-sized planetesimals? And I cannot talk so much about that. That I think is due to the streaming instability, but that's for another talk. I want to focus on the next two stages here. When we have the planetesimals, how do they grow to form planets? And also, as you see here, this is a potentially habitable planet here with water. Sort of what are the surface and atmosphere conditions on young potentially habitable planets? So what are the atmospheres that come out? And of course, the atmospheres are connected to all of this process here also. So habitability is connected to formation. Now, planet formation cannot take forever. It takes place, it's a race against time, because it takes place in these protoplanetary disks that exist around young stars. These pictures are done with the ALMA telescopes. These are young stars photographed in millimeter wavelengths. That means we don't see the star as much in these wavelengths, but what we see is the thermal emission from dust orbiting around the star, which has been heated to maybe 50, 100, 150 Kelvin, and then it's re-emitting sort of in millimeter and centimeter wavelengths. And you can see basically all young stars that are within a few million years old that you point your telescope at will be surrounded by these protoplanetary disks. You can show that these particles have grown to millimeter sizes. They're not micron sized anymore. You can analyze the SED, the spectral energy distribution, show that these are millimeter, maybe even larger in size. So that you're already seeing here the first stage of planet formation. This is not micron dust, already grown dust. They have typical sizes of 100 astronomical units, so sort of similar to the solar system. They contain 99% gas also, which we don't see. Hydrogen and helium has no opacity to speak of in these temperatures. And as I said, 1% dust and ice particles. Now, these pictures are nice. What you can also do then is that you can study whole star-forming regions. You can study young stars of different ages. And then you can see as they progress in age, how many of them still have a disk around, or how much mass is in this disk. And that's what this plot is showing from Dichotomy in 2018. So it's a scheme here where you have class 0, class 1, and class 2 young stars. And you just think about this sort of very young stars, maybe 1 million years old and a few million years old here. So all young stars, but different ages. And you see a strong evolution here in the amount of dust that's detected in these disks. So this has the logarithm of the dust mass in Earth masses. 1 Earth mass, 10 Earth masses, 100 Earth masses, 1,000 Earth masses. 1,000 Earth masses is a lot of dust, right? So a lot of stuff to make planets from. You see, we should check the 50% probability line here. You see that the young disks that are sort of between maybe up to 1 million years old, they have from several hundred Earth masses, basically maybe up to 1,000 Earth masses of dust. But as time progresses on, particularly in this class 2 stage that are disks that are young stars that are a few million years old, it's already fallen drastically down to a few Earth masses. So something happens over a short time. That's why we say planet formation is a race against time, because both the dust and also the gas is accreted onto the star. So you should imagine that the gas that we don't see here is moving onto the star, feeding the star, and the dust grains at the same time are drifting onto the star maybe a little bit faster than the gas even. So we have a limited time to make planets. So both planetesimal formation and planet formation must occur within a few million years when there's still mass left in the protoplanetary disk. Now I showed you these pebbles from the lab. This is what we think is orbiting around here. And the first thing you can ask yourself is, yeah, maybe they all turn into planetesimals, like this arrow cross. This is a planetesimal from the Kuiper belt. So maybe that's a good starting point. That's sort of the starting point for classical planet formation. I would say everything turns into planetesimals. They collide in a dry way, and then magically we should get planetary systems out. The issue is that this doesn't work so well, and I'm illustrating it here. And this is from a paper that I wrote together with Bertrand Bitch in 2019, showing why planetesimal accretion is not very efficient. But let's start here. This is a classical n-body simulation from Tanaka and Ida from 1999. It shows you what happens when you put a planet into an ocean of planetesimals, and the planet is migrating. It's migrating in. You see here, these are some weird arbitrary scale natural units. You shouldn't care too much about, but the planet is migrating towards the star this way here. And you see that the planetesimals in front are not getting accreted. They're getting pushed in front. Some of the planet is passing over some of them. And in the end, when the planet is moving through here, it doesn't really accrete very much. It sort of plows through these planetesimals and scattering them around, but it doesn't accrete them particularly well. Now, in this paper from 2019, Bertram and I, we took this model and we took sort of and parameterized it, and we put it into a simple growth model. We say, how far can you really grow with this method? And we try to push it. So we say, let's be very generous and make 1,000 Earth masses of planetesimals in the solar system. That's a lot, really a lot of mass. You can hardly imagine to have had more. And I don't know where all this mass would be today either. But let's put in 1,000 Earth masses, and then we can start our growth here. We want to match here Jupiter, Saturn, Uranus and Neptune. So here's the distance in AU, and here's the mass in Earth masses. So Jupiter here, 300 Earth masses, 5 AU. We can try to start to form Jupiter. And that's what these tracks here are showing. So we start at 5 AU, you're growing, and then you start to migrate towards the star also because of the gravity torque from the surrounding gas. And you can see that, okay, we can sort of grow something that becomes like sitting at 1 AU or 2 AU or maybe up to 2.5, 3 AU there. But that's really not something similar to Jupiter. That's more similar to hot Jupiters that are observed around other stars. But then you can say, okay, then migration is the problem, so we can start a bit further out. We can start at 10 AU. Then we have room to migrate over, but then the growth rate is so low, so we cannot really do much. I should show you what the different colors are. This is our basic assumption that planetesimals are 50 kilometers in size. We can make the planetesimals smaller. Then they tend to be more affected by gas drag and have a little bit smaller scale height here. They're not lifted so high, and therefore they're a little bit easier to accrete. That's the red one. That helps a little bit. We can also make the migration a little bit slower. That doesn't help at all. If the planet doesn't migrate, it doesn't encounter any planetesimals. So it's a real issue here. And now you see here Jupiter. You look at Saturn. We're missing Saturn entirely. And then you look at Uranus and Neptune. We try to start at 15 AU and 20 AU, and it's completely hopeless. So there's a real issue, I would say, with the classical view that pebbles turn into planetesimals, turn into planetary systems. And this is actually not new. We were just confirming basically this paper and a handful of other papers that had written about this before. And of course, a lot of people were aware of it, and that's why we and others started thinking about alternatives something like a decade ago. And what we came up with is this theory of pebble accretion, which I will mainly focus on from now on. And pebble accretion is contrasted to planetesimal accretion in a very simple and illustrative way. If you have a protoplanet here, this one here, which is growing, it can accrete a pebble or it can accrete a planetesimal. Now, if it tries to accrete a planetesimal, most of the time, it's a pure scattering problem. It's a sort of a two-body scattering problem, or with the sun also. It comes into the hill sphere, it gets scattered around, and the planetesimal is now on an eccentric orbit, which makes it harder to accrete next time it comes around, unless it's very small and it gets circularized again. So this is a real issue. Now, what happens to the pebble instead? It comes in, it feels now, it loses energy. Both the pebble and the planetesimal are formally gravitationally unbound down here. They have a positive energy relative to this growing protoplanet. But as the pebble is scattered by the protoplanet, it runs into the gas. Gas is slowing it down. It's draining energy out of the pebble. At some point, the total energy of the system is negative. The pebble is now formally gravitationally bound to this planet, and it has no choice but to spiral in and become accreted by the planet. That is sort of the essence of the streaming instability of pebble accretion here. This is from the original paper we wrote in 2012 about pebble accretion, where we also showed it hydrodynamically. We did an actual simulation of this. You see here, the dust is moving around. You see from the top here, you see from the side here that it's sedimented. We turn on the planet at this time, and you see these very strong accretion features, and the planet basically vacuum cleans everything in the box within a few years. So pebble accretion is a very efficient way to get material into the planet, and this can only occur because there's gas slowing the energy, slowing the pebbles down, basically taking away that excess energy that prevents the planetesimals from getting accreted. Okay, I want to just show you quickly how to stop pebble accretion before we continue with showing planetary populations made with pebble accretion. So what happens is that this planet that's going along here is happily accreting pebbles as long as it's not very massive. As it becomes more and more massive, it starts to perturb the gas disk. This is the pressure gradient in the disk around. High pressure close to the star, lower pressure further out. That's the negative pressure gradient here. That's actually driving the pebbles to move constantly towards the planet. At some point, the planet starts to make a little bump, a little gap in the protoplanetary disk. It makes a little pressure bump on the outside here. And this pressure bump on the outside in the gas that will attract the pebbles and prevent them from crossing over the orbit of the planet. I can show you here also in an actual simulation. So this is a simulation of a planet, a hydro simulation. It goes over 2 pi here in the azimuth. So this is supposed to be like an annulus. You just put it in a box here. This is the distance from the star, one being the planet distance. You see the planet coming in here. You see the sort of gravitational features that it's made in the gas here. Actually, this is the dust collecting these gravitational features. And you see that now there's after a certain mass, there's a lack of pebbles here. And the pebbles that are drifting in from the outside, they are piling up on the outside of the bump here. But the planet is not accreting pebbles anymore. You can see it in a different way. You can see that the whole protoplanetary disk, as a function of the distance from the star here, the disk is actually orbiting a little bit slower than at the Keplerian speed. The gas is a bit slower. Why is that? Because if you take a gas element out here that's orbiting around the star, it feels both the gravity force of the star that will make it move Keplerian, but it also feels a pressure gradient. That high pressure here, low pressure here, and that pressure gradient acts a little bit like a reduced gravity. So that means that the gas will orbit overall 0.5% slower than the Keplerian speed. That's what we're seeing here.
Some kind of secondary planet formation. So
you could maybe make planetesimals here if you pile up a lot of material there. That's certainly an option. Yeah. And then what happens when you go up in mass now? 20 Earth masses, 30 Earth masses, 50 Earth masses here, that at some point here on the outside, there's no pressure gradient. There's a 0 pressure gradient here. That means the gas will start to move at the Keplerian speed, which is the 1 here. So at some point you get enough that the gas here is moving at the Keplerian speed. When the gas is moving at the Keplerian speed, then the particles don't feel any headwind from the gas anymore. They're not moving towards the star anymore. So the particles will then pile up here. All the pebbles will pile up here. That's what we call the pebble isolation mass. And you can sort of make a simulation of that and the analytical scalings, and you can find out that the pebble isolation mass is something with the disk aspect ratio cubed and then some factor in front, and you get something like at 1 AU with sort of 10 Earth masses-ish or something. And if you go further out, it becomes higher. If you come further in, it becomes lower. Yeah. And I should also say that the pebble isolation mass comes before you make a real gap in the gas. It becomes at some point, you can show that it's when the gas density here has been reduced by 15% relative to the unperturbed density. When the planet grows more and more, it'll make a deeper and deeper and deeper gas gap. And that will actually affect the migration rate. I'm going to show that in one of the next slides. All right. So now we can see if we can make the solar system with pebble accretion, and that goes far better than with planetesimal accretion. Because we can now start, because pebble accretion is quite efficient, quite far away from the star, we can start out at 25, 30 AU here. And then we can grow up, and we can see I have 2 growth tracks here. One that goes the blue one, and one which is the red one. And the difference between them is that this one is a metallicity of 1% dust in the gas, and this is 2% dust in the gas. And you see at 1% that you're growing happily, and then you're migrating, and at some point you reach this pebble isolation mass here, which is the line that I'm crossing here. And at that point, when the pebbles are not accreted by the planet anymore, then it doesn't have any energy source. While the planet is accreting pebbles, there's a lot of accretion energy put into the planet, and that prevents any gas from being accreted onto the planet together with the pebbles. Once you stop accreting the pebbles and there's no energy from that, then the gas around the planet can start to cool down and then become accreted. First, it becomes accreted quite slowly, and at some point it becomes accreted very fast. Yeah. When the self-gravity of the gas becomes important. So then there's a runaway gas accretion. And we can see we can park one planet here at 2 AU, and we can park another one here at 5 AU, have a little bit higher metallicity. Yeah. There's another effect in this, that is actually as the planet is growing up, and here, as I said, here you have something like a little bit of a gap forming, and you become more and more massive, you make a deeper and deeper gap. And that deeper and deeper gap also means that the gravity from the disk on the planet becomes weaker and weaker and weaker, and therefore the planet is not driven to migrate into the star anymore. And therefore, the migration stops also. So it's also, you can sort of grow over this planetary migration problem. So we've shown in several papers now that planetary growth by pebble accretion actually outperforms the migration, and this is a way by which planets can migrate towards the star, and yet they can end up in orbits that are pretty far away from the star. So that was sort of to make giant planets. That works pretty well now with pebble accretion. We're not going to the inner solar system and see what happens there. So anything that is, so we have the protoplanetary disk, and these pebbles are sort of drifting in. They're feeling the headwind. I said this, the gas is a bit slower than the Keplerian speed. The pebbles are feeling the headwind. They're moving. They're losing angular momentum. They're moving towards the star at an enormous flux, actually several hundred Earth masses per mega year. So if you're sitting in the sort of region here up to a few AU where terrestrial planets form, we know today we only have a few Earth masses of solids here, but this region must have been traversed by hundreds of Earth masses or pebbles drifting past. Yeah, and this can have several different consequences. So we explained one of them in this paper by Lamprecht in 2019, and that is that we tested what happens if you have different fluxes of pebbles coming through the disk. We started sort of with a few 10 Earth masses per mega year, and we upped it up to something like 100 Earth masses per mega year. Let's start with a low pebble flux. Let's assume there are not that many pebbles passing through the inner solar system. We started our embryos here. There's a real N-body simulation between a half and a few AU, and you see that they're growing, they're starting to migrate, and they're not affecting each other. They're sitting just like pearls on a string all the way up. And after 3 million years, this is what we're left with. And then you can run it for 100 million years, and then you get something that looks very much like classical terrestrial planet formation. You have a number of point a few Earth mass objects that are colliding with each other, and after 100 million years, you form something that has characteristic mass of Earth and Venus and Mars, maybe also. So it's sort of where you see classical terrestrial planet formation emerging out of here. But now we can actually vary and say, well, this was a quite low pebble flux. We can up it up to 100 Earth masses per mega year. That's what this one said. And then you can see they're continuing to grow. They are migrating a lot more now, and a lot of these tracks are stopping now. That's when the protoplanets are colliding with each other while they're growing. And you end up with these systems here of super Earth planets that are 2 to 10 Earth masses, so much more massive, just by increasing the pebble flux just a little bit, because the growth rate becomes much more higher then. Yeah. Again, you can run it after the disk is gone. You can run it for 100 million years, and you can see that you are left with these systems of you get some hypergiant impacts between planets that are few Earth masses in size, and you go up to maybe 10, 20 Earth masses here, which looks a lot like some of the super Earths that are observed close to the star in this Kepler data that I showed you early on. Yeah. Let me make this point actually also. That is that if we look at the period ratio of planet pairs in the Kepler data, you look at the Kepler data, that is this green line here. There are almost no preferred period ratios at all. It's like there are very, very rarely planets that are in resonance. And that's actually in contrast with this model, because a lot of these, when they migrate in, they tend to migrate into a way that they sit and they are sitting in various planetary resonances where the orbits are integers of each other. You can see there's a resonance here, 2 to 1 resonance here. There's a 3 to 2 resonance, 4 to 3, 5 to 4. And if you look at the data here of this one and this one, you can see that they are sitting very strongly. This is a cumulative plot here. They can see they're sitting very strongly, particularly this 4 to 3 and the 5 to 4 ratio here, and also a little bit in the 3 to 2 ratio here, because they sort of go up and they're sitting on these lines. And this is a typical consequence of planetary migration. The planets migrate into resonances. Now, the funny thing is that after running it for another 97 million years here, then there are so many instabilities, the planets collide with each other and so on, that these resonances are completely gone. So when we then run it through this N-body simulation for 100 million years, then you see you end up with this line, or with this line that looks a lot more like the Kepler data. So traditionally, the sort of lack of resonances in the Kepler data has been used to argue against migration. So, planets don't migrate since they're not in any kind of resonances. And now we can see, yes, but they can actually form in resonances here, and the resonances will be broken naturally just because the planets are too close to each other. They're not going to survive in those resonant configurations. All right. So we can also now make whole planetary populations. I showed you how to make gas giants, super Earths, and terrestrial planets. Now we can make whole planetary populations. We can pick random starting times, random starting positions of the planetesimals, and then we can basically sample it, and then we can make a map of where the planets end up, function distance from the star, and this is the mass. And you see here something rather nice, that we end up with very distinct populations here that are recognizable. We have gas giants up here. We have, what else do I want to say? We have terrestrial planets and super Earths down here. If nothing in between here, that's because once you start to accrete gas, the pebble isolation mass is lying approximately here. That's when you start to accrete gas, and once that happens, it happens fast. So it's very hard to be 40 Earth mass or 50 Earth mass. Not a very likely mass to have. So we can see all these nice categories of planets, but you also see something a little bit less nice. If we want to match the solar system, Jupiter, Saturn, Uranus, Neptune, we are not doing it too well here. It's a little bit away from it. And then we can play around with some parameters. We can increase the metallicity of the dust to gas ratio in this from 1% to 2%. And then you can see you're actually doing much better. Now, Jupiter and Saturn are lying on this natural growth track, I would say, or something that forms far out, grows and migrates in. And you can even see Uranus and Neptune are maybe a little bit above that, but it's very likely that Uranus and Neptune form further in and then migrated out later on by another mechanism. We can also say there's another issue in this, that is, if you look at the composition, these blue ones are more than 30% water, not on the surface, but bulk. Remember, Earth on bulk water is just a few hundred ppm probably. And this is too much water here. You see Earth and Venus are forming here, but they're too much water. But if you make the disk model a little bit different and we make it a little bit hotter, where the ice line is sitting further out, then we can get Earth and Venus here to form somewhere where they're not particularly wet. They don't become ice planets. But one thing, so now I'm going to talk more about rock planets. One thing that came out of this study is the incredible ease at which you make terrestrial planets with pebble accretion. It's like super easy. It's sitting, the mass and radius are easy to form. Gas giants are hard. Super Earths are a little bit hard, but terrestrial planets are not hard at all. So that's why we want to, in the last 5 years or so, start exploring whether Earth and the other terrestrial planets formed by pebble accretion also. That's what we will turn to now. Before I show you more theoretical evidence that Earth could very well have formed by pebble accretion, we can also go and ask ourselves, is there any evidence from our own planet or from the meteorites that the Earth formed by? In what way the Earth formed, I would say. Yeah. And one observation that people who study meteorites make is that if you study the isotopic, so let's say here that the building blocks of Earth can be inferred by comparing the isotopic composition of major lithophile rock-loaming elements. Why lithophile rock-loaming? You want the elements that are present in Earth mantle, not the ones that are hiding in Earth core. You don't know how much of those are missing or not. You want the ones that are fully present in the mantle of Earth. And then cosmochemists, those who study meteorites, they will then study the isotopic composition of various elements. And what they produce are plots like this, where I'm not going to tell you what epsilon means here exactly, but this is chromium, this is titanium. The more you move this way, the more you are neutron rich. The more you have more neutron-rich isotopes, and more this way you are lacking neutron-rich isotopes. So all of these have several isotopes, and if you're plotting up here, you're rich. You have many of the neutron-rich isotopes. If you're here, you're lacking the neutron-rich isotope. The same along this axis here, where we have titanium. And now there are basically two classes of meteorites. There are the carbonaceous chondrites that we believe come from the outer solar system that are rich in carbon. And then there are the ordinary chondrites that are also called the NC chondrites, the non-carbonaceous chondrites. It's a very bad way of labeling them. That's what this guy did in 2011, and people are still sticking to it. So the carbonaceous and the non-carbonaceous. And the funny thing is, when you plot along these kind of two isotope plots, you tend to have the carbonaceous chondrites in one area, and you tend to have the non-carbonaceous or ordinary chondrites in another area. So clearly the solar system had two different isotopic compositions. And this can be used to infer what the Earth is made out of. Because what you see here is that Earth and Moon are the same, and Earth typically plots in the NC group, the inner solar system group. Makes sense, we are in the inner solar system, right? But Earth also leans to the outer solar system. And it does this in several isotope systems. Maybe it's even more clear here in calcium from Schiller 2018, where you have the inner solar system meteorites here for the neutron poor isotopes, and then you have the neutron rich isotopes here. Again, you have Earth, Moon, and Mars also leaning always towards the outer solar system composition. And this is very exciting. Now, this can be interpreted in several ways. One way this can be interpreted is you can say, well, it doesn't matter where Earth is sitting between these two, because Earth is clearly not looking like this. It's not looking like this at all. So Earth must have formed out of some isotopic reservoir in the solar system that we don't sample with our meteorites at all. That's a valid thing to say, that there was a third group of planetesimals in the solar system which was plotting here, and Earth accreted all of them. But then that's fine. but maybe we don't learn so much from this because then we are saying that there's an unseen planetesimal reservoir that made Earth. We're saying the Earth formed out of planetesimal similar to Earth that we don't have any samples of anymore. Another interpretation, which I favor very much, is to say, look, this is clearly the Earth is forming from a mixture. Earth is sitting on a line between here and here. Yeah, so Earth is sitting on a mixture line between here. Maybe Earth started by creating this material and later on creating this material. And how do you get material from the outer solar system in to feed Earth? Well, with small pebbles is the obvious explanation. So maybe this is a quite strong support for pebble accretion. Okay, now this is very, very debated at the moment. The origin of this great isotopic dichotomy and what it means in terms of forming the Earth. And I should show here that there are two interpretations, both of why there's an isotopic dichotomy and also what it means in terms of Earth formation. Now, I talked about neutron-rich and neutron-poor isotopes, and actually anything that's very neutron-rich is typically something that's nucleated in a supernova explosion. In a supernova explosion, you have the R process driving very high neutron fluxes that drives everything toward neutron-rich. Yeah, so everything that's neutron-rich probably has to do with grains from supernovae coming in there, right? So one interpretation of this dichotomy is that the solar system started forming actually with something that was fairly rich in neutron, in dust grains condensed in supernova explosions. Yeah, and then at some point on the inner solar system, there was an additional infall of something that was depleted in supernova grains. Yeah, then you get an inner composition that's depleted in supernova grain and outer composition that has more supernova grains. And then they would say, and then Jupiter formed at some point, and Jupiter prevented any mixing between these two components. That's why we have the non-carbonaceous chondrites on the inside and the carbonaceous chondrites on the outside and nothing in between. Now, another interpretation, which was proposed a while ago, and which we also explored in a paper last year, is the following: that actually the whole solar system was of the outer solar system composition to begin with, but something heated the inner solar system, maybe an FU or Ionis outburst, something hot heated the inner solar system and destroyed some of those grains that carried supernova nucleates in it. Yeah, so the inner solar system became supernova grain poor, and the outer solar system is of normal composition, so to say. Yeah, so that's the sort of difference in these two views. But what we showed in this paper, and what we also showed, what Stamler also showed in this paper here, is that if you believe in this model and say, well, Jupiter blocked everything. Jupiter forms here after a million years, it blocks everything. Nothing can drift in, it just ends up outside of Jupiter. Then we also show, but then nothing stays inside of Jupiter either, because of this drift of the pebbles. All these pebbles are just drifting in, and you would never be able to form anything inside of Jupiter. And what we proposed instead was to not worry about how to separate these two components at all. We proposed more a dynamical picture, where initially the solar system is separated in an inner composition and an outer composition. These blue pebbles that carry the outer composition, they're staying on the outside, but after a while they're drifting in. And then you see after a few million years, they're drifting in, and the composition in the inner solar system changes from inner solar system to outer solar system composition. At this point, you're forming some of the ordinary chondrites that look a little bit like a mixture, and you're also forming proto-Earth and Mars here, first by creating this material, and then later on by creating maybe 30–40% of this material here from the outer solar system. And then in our picture here, we would say that because Earth actually looks like a mixture of inner and outer solar system composition, there's no reason to require Jupiter to block the flow of pebbles. And also all simulations now are indicating that Jupiter will actually not block the flow of pebbles. The reason is that the pebbles are coming in, and I said you had a pebble isolation mass, then the pebbles cannot pass anymore. But small dust fragments can actually. So if the pebbles are lying out here colliding with each other, when they turn into micro-sized dust, they're very easily making it past the gap, and then they're becoming then they're growing up to pebble sizes again, and that's basically what Stamler showed now in 2023. Okay. See if I have more about this. Yeah, I wanted to show a little bit about what's happening now, because it is a great debate now about whether Earth formed by a mixture of inner solar system composition or not. It's also a debate about whether Jupiter blocked the flow of pebbles. And one thing that's been missing from the measurement so far is actually silicon. I'm not a cosmochemist, so I don't fully understand why it's very hard to measure silicon isotopes, but it's down at very, very low variations between the inner and the outer solar system. And now there's a paper coming out from the cosmochemistry group at the University of Copenhagen, where they measure silicon isotopes, again, enriched in supernova isotopes and depleted here. And you see here very beautiful, very small error bars. You see the sort of inner solar system here. These are the differentiated meteorites, completely depleted in supernova. grain. The outer solar system here on the outside, Earth is always plotted at 0 by definition, lies in the middle here. And again, you see Earth sort of lying on a very nice mixed line between the inner and the outer solar system. They could even make a timeline of the solar system where you plot here as a function of the composition, neutron poor, neutron rich, and this is the time at which the certain meteorite parent body accreted. 1 million years, 2 million years, 3 million, 4 million years, you see very clearly there's a succession of compositions coming with time, start being very neutron depleted, then more neutral here when this ordinary chondrite form, and then in the end you get the outer solar system composition coming in. And this is actually in complete agreement with this picture here, and it's completely inconsistent also with Jupiter blocking the pebble flow. Then there's no reason why there will be a temporal change to the composition of the inner solar system. Okay, that was a bit about cosmochemistry. Let me get back to the planet formation theory, because now I think I've shown you pretty good evidence that we can form Earth and Venus, other terrestrial planets by pebble accretion. I also shown you cosmochemical data that agrees with it. So then I think it's a very good reason to explore it more. What are the consequences of forming Earth by pebble accretion? Well, a direct consequence is that Earth formed by pebble accretion would take only a few million years, whereas Earth forming by planetesimal accretion, I showed you how these blue planetesimals that were a few Earth masses turned into Earth and Venus over 100 million years. That's fine. That's just a timescale issue. But there's a very important implication for volatiles and atmospheres in the origin of life. That is that the volatiles, they will live completely differently in these two pictures. Now, in the first picture, planetesimal accretion, Earth forms dry, like this one, and it collides with a few icy asteroids from the 2-3 AU region, and this eventually gives Earth its water. And when you run these simulations, it almost looked like a log normal distribution. This is from Raymond et al. 2004. The amount of oceans accreted to various planets in those simulations are somewhere between less than 1 and more than 100 Earth oceans. This is fine, but for me, it's also completely impossible to work with. It's a stochastic theory, and it has no prediction power whatsoever. It may be what happened, but I don't think it's what happened, and I don't think it's very useful for making any predictions about habitable planets if it's that random. Now, with pebble accretion, it becomes very, very different, because now the volatiles are delivered via pebbles, and the pebbles are not stochastic. They're so small that you know how much pebbles is coming into Earth. It's not a stochastic value anymore. The pebbles have rims here of water, and you can see as the pebbles are raining down, this water will rain into the magma ocean. This way, with pebble accretion, you actually calculate exactly the amount of volatiles that comes into Earth. Yeah. I'll get back to that point. Let me just show you when we explore more terrestrial planet formation with pebble accretion. So this is our paper from 2021, which Helmut is a co-author of. And we had a very good discussion in Copenhagen at some point, ironing out all the details and so on. One thing that's actually kind of striking about the inner solar system is that there's a little bit of an order. There's a big Venus and a big Earth and a small Mars. It looks a lot like the outer solar system, and there's a big Jupiter, a little bit smaller Saturn, and small Uranus and Neptune. It looks like a pebble accretion growth track. The further out you are, the smaller you are, basically. Now, this is a little bit sort of dodgy, maybe, because you see that I was cheating you here. Earth is not small. Earth is not smaller than Venus. It should be smaller in this picture, right? So Earth is actually bigger. But if we believe there's an impact that forms the moon, then you're fine, because we know the moon has the same isotopic composition as the Earth. Earth must have collided with something that was quite similar to Earth and maybe quite massive also. So here we form an additional planet of 0.4 Earth mass. Here Earth becomes 0.6 Earth mass. We do something on 0.4 Earth mass. We say later on this will collide with that, and then make Earth. Yeah, and we call it Theia, and that's going to form Earth. But then we can make a model now where we form Venus, Earth, Theia, and we form Mars. We form Venus, Earth, and Theia early. They grow up. The red line here is the planetesimal contribution, because there are many planetesimals to accrete. And you can see something like, let's just start with Mars. We found Mars a little bit later. That's why it doesn't grow so much, why it doesn't accrete. Start with Mars. Here you see when Mars is finished forming, it's 0.1 Earth masses, and half of this comes from planetesimals. So Mars is not such really pebble accretion object. It's more like a mixed object, so to say. But if you go to the planets that form earlier, after they sort of reach 0.1 Earth masses, pebble accretion takes over, and in the end they become dominated by 70, 80, 90% pebble accretion and 10% planetesimal accretion. Yeah. Yes, I guess I can just show you here are, of course, our major fit models. We know the result. We get the right initial conditions to make the planets. We can vary around a little bit. The one thing that we did here was that we started all the planetesimals about 1.6 AU. It's the only way we can make a growth track. If they start everywhere, there's no reason why you'd be sitting on a specific growth track. So we simply say there's something that makes planetesimals early on at 1.6 AU, and we can vary that. You can see here we can vary where they are starting exactly. We can vary the starting times, and these are the population plots that we get out of it. So something growing in situ and then migrating in, and we see we match Earth and Mars, and we know it quite well here. Then we can also say, no, let's form them randomly everywhere. These planetesimals are not in a specific place, and then we still sort of match Earth and Venus and Mars, but they're just sitting all over the place. We could have had any mass anywhere, so to say, right? We can also increase the dust to gas ratio a little bit, and then we go sort of from forming Earth planets to more forming super Earth. Just wants to show you a little bit of parameter variation that can happen when we choose different parameters. Okay, but let's just get back to the volatiles now. Now, an important thing is that if you do a hydro simulation of a planet that's sitting in the center here, that is embedded in the protoplanetary, the gas flows will look something like this. So this is the Hill sphere of the planet, the radius over which the planet can affect the gas flows from the protoplanetary disk. And you see that on the outside of the Hill sphere, you get flows from the protoplanetary disk coming in and then moving out again. So this is something called horseshoe orbits. We call them recycling flows also. But you can see that just because a pebble comes into the Hill sphere doesn't mean that it's not affected by this flow yet. Now, when you go further and you start seeing circulating flow, and the circulating flow is actually the envelope that's bound to the planet that's not in any contact with the horseshoe flows outside. So that's where this sketch comes from, basically, that the pebbles are sort of raining down, and the first here's 1,000. So they start from inside. Here's the planetary surface by the magma ocean. I'll come back to that. And then when you go to 1,000 planetary radii, you get the Hill sphere that's basically out here. And actually, the first 90% of the Hill sphere is dominated by these recycling flows. Yeah. When you come below that, then there's a factor of from 100 planet radii down to 1 planet radius, approximately where you have a bound envelope, which is what I'm showing here. And our volatiles are very affected by the temperature increase here because it gets hotter and hotter as we move closer and closer to the star. In this case here, you can see we can put the water ice line. So the water ice line is the temperature at which, above which water ice will only be present as water vapor, and you cannot really accrete water vapor. So you need water ice. And it was like the ice line in the protoplanet disk was likely at 0.7 AU during most of the disk lifetime. It's a bit strange because if the Earth formed at 1 AU and the ice line was at 0.7 AU, you should have 30% water on Earth or something, which we don't have at all, right? But we explain that here by saying as the pebbles are raining down, at some point they're going to reach a temperature that's this 170 Kelvin here. They're going to reach it already in this recycling area out here. And that means that all of the water vapor that gets blown off, then it's transferred back to the protoplanetary disk. And this way you have a very good way of reducing the amount of water that the planet accretes here. And this happens at around 0.01 Earth masses. If you're less than 0.01 Earth masses, you're so cold at the surface that you are basically growing up and becoming icy and small. And any pebble would just land there and not lose any of its ice. Above 0.1 Earth masses, you start having this effect coming in, and then you're losing water on the way down. So you can make a model now of volatile delivery on Earth, where you take a model where the Earth grows to 0.6 Earth masses here, and you say, what is the mass fraction of the planet that is now in water? And early on, until this magical 0.01 or 0.0 few Earth masses, the water fraction is just increasing and increasing. We start with the dry planetesimal, and we're just accreting a lot of water with pebbles up to 10% water. So really, really water rich, way too much water. But then after 0.01 Earth masses, since we are accreting dry from then on, then we're just reducing the amount of water all the way down. And we end up with something that is like a few thousand ppm of water. Now it's a little bit high. If you look at the Earth oceans that are plotted here, they are a few hundred ppm of water. But probably there's 10 times more inside the Earth core, maybe not so much in the mantle, definitely in the core. So we think that Earth water, total water body is probably lying here. And we can see we are hitting Earth's total water body pretty well with this model, actually. Now, what about carbon and nitrogen? Carbon and nitrogen are major atmosphere constituents. Also, we need to understand where they're coming from. It's also very important for the origin of life, clearly, right? Carbon and nitrogen are actually present in organics. If you study meteorites, you will see carbon and nitrogen being present as organic molecules. And of course, they will never survive into the magma. These are not going to be the origin of life molecules. They will drown in the magma ocean and just turn into carbon again, basically. But particularly when you're heating, Geil and Trilov did experiments actually with analysis of heating these kind of organics. And when you heat them up to between 300 and 400 Kelvin, a lot of them sublimate. And then there's a bit of graphite in it also, maybe 10% graphite, which is more refractory, which burns at around 1100 Kelvin or so. So you make a similar theory now for carbon and nitrogen as we did for water, but it's not destroyed at 170 Kelvin. It's more destroyed at 300-400 Kelvin, so at a little bit higher temperatures. And then we can take let's look at the carbon content here. We take a few thousand ppm of carbon. That's very, very high. It's sort of the same as it is what we find inside of the meteorites. And then we can grow Earth, and when we come to something like 0.0 a few Earth masses, then we start to destroy the carbon in the envelope here. It turns into CO2, methane, and other really, really, really volatile molecules that are just going to diffuse out again and not become accreted. And then we can say we can reduce the amount of carbon that we accrete down to a few hundred Earth masses. And again, how much carbon do we want? Well, we can see how much is in Venus's atmosphere. If Venus has like 100 bars of CO2 in its atmosphere, that gives something like a few 10 ppm of carbon. It's not very much. But again, inside the core of Venus, the core of Earth probably store a lot of carbon. So the really carbon budget of Earth is probably a few hundred ppm, and we see we're pretty much matching that there. And we can do it with the nitrogen also. So you can see that the nitrogen to carbon ratio is not very high in the meteorites, sort of 1 to 100 or something. So we start out with 10 ppm. We want to reduce it to somewhere. Now, nitrogen is nice because there's probably not so much nitrogen in the Earth's core. It's all sits in the atmosphere. There's probably a little bit in the mantle. So maybe Venus's atmosphere nitrogen is a little bit better. That sits at a few ppm. We want to be somewhere between Earth and Venus here. And we see with the nitrogen, we're actually pretty much arriving in the right ballpark also. So this sort of pebble snow idea that the pebbles are snowing down and then losing their volatiles on the way down actually gives a pretty good match to H2O and to C and to the end contents of Earth simultaneously.
Yeah, maybe we should slowly come to an end.
Yeah, I have a few more slides.
Like 5 minutes.
Yeah, 5 minutes is perfectly fine. Yeah, okay. So we can also look at what happens to the planet itself because it gets immensely hot. I was showing you using this sketch with the magma ocean already. And what happens with time is that because we want the planet to differentiate also at some point. Now, traditionally, people have said something like Earth and Mars and Venus are differentiated because there were giant impacts. Those giant impacts have melted the planet, and then the iron separates from the metal and then sinks into the core. Yeah, and on top of that, so you have a giant impact, and then it gets thermally blanketed by a runaway greenhouse atmosphere, and this would then form magma oceans. Now, with pebble accretion, you don't really need giant impact. You just need to have this immense pebble accretion energy. Because this is a timeline that goes around here 1, 2, 3, 4, 5 million years. It's just the size of the planet is normalized to the instantaneous size. Maybe I just want to show you here basically that you start out being not molten. So 1 is completely molten and black, red is completely molten and black is not molten at all. You start out accreting a primitive body that is not molten at all. And at some point, actually, there's an early differentiation, which you see here also. This is the mantle, this is the core. That's because of short-lived radionuclides like aluminum-26 that forms really early that will make that would differentiate it already when it's sort of a planetesimal. But then as you're moving forward in time here, you can see that you're accreting a lot of material here, which is not molten, which we're seeing here. But then basically, at some point, the accretion heating becomes so immense that you release an atmosphere. All the water sitting at the surface becomes vaporized. It's a runaway greenhouse effect. And that gets the surface so hot that the surface melts and separates the mantle from the core material, and the differentiation itself also makes additional heat contribution. So from that point on, this is like 0.01 Earth mass up to 1 Earth mass. You are completely molten. So this way you get very, very natural differentiation of planets when they accrete when they form by accreting pebbles. Okay, let me just skip this part here. Just gonna go to sort of the last couple of slides because I promised you also I would look a little bit at the atmosphere. Yeah, and so we did a model that we presented in this paper that will come out in astronomy and astrophysics soon. We basically took all the volatiles that we accreted and we distributed them between the core and the mantle, between the mantle and the atmosphere. Yeah, so a lot of the volatiles are actually siderophile, that they prefer to be with the metal in the core. They have a tendency to be in the metal, maybe by factor 10. They want to have a factor 10 higher concentration in the metal that they want to have in the mantle. So if we look at our Mars model here and our Earth model here, let's just start with what goes into the interior. So this is the hydrogen in the interior, this is the hydrogen in the core, and this is the hydrogen in the mantle. Here's the Earth oceans. So we accrete, and after 5 million years, the planet is stopping to accrete. I say at that point, actually, there are like 10 Earth oceans of hydrogen that enter the core of the Earth. So the core becomes the main hydrogen reservoir. the mantle gets very little hydrogen, because when the magma ocean crystallizes, when you stop accreting after 5 million years, the magma ocean crystallizes and then it spews out all of its volatiles that are not in the core, and then it comes out into the atmosphere. Here is what I want to show here. Yeah. Now, there is another, when you want to know what goes into the atmosphere, you have to know how big the planet is, because this is an illustration from Deng et al. In 2020 that shows that a planet which is small, or moon small or something, it will actually outgas a very reducing atmosphere, will not outgas very much O2. It has something to do with iron reactions in the magma ocean, that small planets are dominated by Fe2+ in the magma ocean, therefore they will not outgas a lot of O2, and therefore they will tend to outgas, so you see here for Earth, for Moon and Mars, particularly Mars here, tend to outgas H2 and CO. That's also what you see here from our Mars model. When Mars is outgassing its atmosphere, it gets mainly to be hydrogen that comes out of it. There's not so much oxygen coming out of the magma ocean. It's mainly hydrogen. There's a little bit of water here, but hydrogen is a very volatile molecule. It's very easy to escape by XUV radiation from the young sun. So you see that the hydrogen is sort of being blown away from Mars over the next 50 million years, and it brings along with it all the water. So Mars loses both its hydrogen and its water, and its CO and its CO2, because the hydrogen is just dragging along everything. If you become a more massive planet, then this ratio here changes. The Fe3+ or Fe2+ ratio changes. You outgas much more oxygen from the magma ocean, and you tend then to outgas less hydrogen and more water. Now, this hydrogen is very little, it still escapes, but there's so little of it that it cannot really drag along any of the other molecules. This way, the Earth here maintains a few Earth oceans of water, and it maintains its CO2 atmosphere also. This, by the way, what goes on in the interior of the Earth. Again, you see something like 10 Earth masses, 10 Earth oceans of water in the core, and actually something like 10 Earth oceans of CO2 in the core also. So most of the carbon and hydrogen end up in the core. But it's very interesting here that more massive planets like Earth experience this kind of mantle oxidation, that you get a more oxidized magma ocean that outgasses more O2, and this leads to the outgassing of an oxidizing atmosphere. So just sort of a final slide. So we now went all the way from pebbles to the magma ocean and outgassed a first atmosphere. And the question is, what do we care about atmospheres in a way? Right? It's very interesting if you study atmospheres, but on the other hand, atmospheres also have a clear implication for the origin of life. So as I showed you here, Mars likely outgassed a reducing atmosphere that was rich in H2, and small planets will do that, I think, but it will also be lost very quickly. And Earth or larger planets will outgas an oxidizing atmosphere that will be rich in CO2 and in H2O. And if you look at the origin of life, it might be very different on such kind of different planets, because people have speculated that when you have reducing conditions like here with a lot of H2, that you're going to have lightning. I don't know if any of you know the board game ÖAW. It's a very fun board game. Really recommend it. You're going to have lightning, and lightning in an H2 atmosphere will be great at producing very reactive molecules like HCN. A lot of chemists will use HCN as a way to produce the first RNA and the first sugars and so on. So that's sort of one way to go about it. On the other hand, if Earth was very oxidizing, then lightning doesn't help you much. If you run lightning through an oxidized atmosphere, you don't produce HCN, you produce NO and NO2 and so on, which is very, very different. But then actually we might be down to these hydrothermal vents at the ocean floor, because at the ocean floor, you're going to have a mantle here which is full with Fe2+, and this can react with water, and that can release actually hydrogen. So you get H2 out of it. So you do have H2 sources even in an oxidizing atmosphere if you go down to the ocean floor. Then you have H2s, and maybe early life was then combining H2 with the CO2. That's a way to produce energy in the hydrothermal vents. So I think it's very important what kind of oxidation state that the atmosphere gets. But I think also we're in a state now where we would like to observe atmospheres around other stars. I don't know if anyone here is involved with JWST projects or ELT projects, but I think it'll be very exciting in the next 10 years or so to see if we can sort of get the first handles on the atmospheric compositions and pressures of planets around other stars. So hopefully we will see a lot of results in this subject here in the sort of next decade. Yeah. Yes, but with that, I will take any questions you may have.
Okay, so now you haven't put an overdose of everything you ever wanted to know about information. And I guess there might be a lot of questions in different areas. So please go ahead.
Thank you for the nice talk. My question concerns the case when we consider formation of the multi-planet system. So you see that the planets of different mass are formed at specific orbital distance. The question is, how specific are these orbital distances? Can you see kind of the fundamental law which connects the orbit? No, I can explain why I ask it, because there are theories which in general consider planet formation in the protoplanetary cloud. And according to this theory, the specific orbits can indeed exist, and they depend on the initial distribution of specific angular momentum and mass density in the disk. And they take into account the fact that when the accretion of the mass elements at in specific planet takes place, so the momentum, the angular momentum of these accreting particles and density somehow change the position of the formed planet, and altogether there might be a kind of the tendencies evolve, which are either arithmetic progression law or the geometry progression law for the orbit. But I'm curious if your theory can come to a kind of such conclusion.
No, I don't believe there's any such law at all, and I've never seen any evidence of it at all. The only law I can think of are resonances. What happens is that as the first planet is sort of migrating in, it ends at the inner edge of the disk, sits there, and then the next planet comes migrating in. But at some point, it runs into a 3-to-2, or first of all 2-to-1, or 3-to-2, or 4-to-3 resonance, where it gets pushed out a little bit all the time. Then this push out can balance the inverse push. So resonances are the only law that I know of, and even resonances are broken relatively easily. Yeah.
Yes, thank you again for that nice talk. I think when a pebble accretion as the hypothesis is the right one in these scenarios, then we have one very interesting aspect, which means that you form terrestrial planets very fast. And I mean, we see also this evidence on these sub-Neptunes and whatever else. That means I would expect then that in the near future, we should discover a lot of Earth mass type planets, but which have kept some primordial atmosphere. Because we did some studies, and we can speak later on going to this to check what should be the mass that such primordial atmosphere, which could be captured during the lifetime of the gas disk, could be remaining forever. And what you showed in your studies here, I mean, it was also with the 60% Earth mass, or let's say 70, whatever, depending on different other astrophysical issues, is from the stage of research now. It fits. We can form the Earth afterwards. But if you would have some Earth mass rocky planet, or let's say 80%, and it depends also somehow on the host star, it could be that the planet remains as a sub-Neptune, but with the mass of an Earth mass or something like that. And if this is the case, then I think there should be many of them, I expect.
I think it depends a little bit on the following. That is that of course, if you put an Earth mass planet into a protoplanetary disk, it will attract a hydrostatic envelope, and it will grow in mass. And at some point, it gets so massive that you can't blow it all up. On the other hand, if the planet is still accreting, if it has an accretion energy, then it's very hard for it to accrete anything. If you look at our Earth mass, it's accreting, they have maybe 10⁻⁵ Earth mass envelopes on them, because that's the hydrostatic equilibrium. Because you will leave it alone for a million years, this might become 10⁻² or 10⁻⁻1 Earth mass. It depends a little bit also on whether you reach pebble isolation mass. Another option is that the pebbles that are drifting in are stopping to drift. At some point, you're running out of them, and the gas is left. Then you might also have your 1 or 2 Earth mass planet accreting a lot of gas. But if you look at our planets here, they don't accrete a lot of gas since they're always accreting pebbles, and you can't do both at the same time, basically. So
maybe we have some other basic questions or some basic questions.
I think it will be a basic question.
Yeah.
So thank you very much for your talk. So you mentioned that, of course, that you can see that pebble accretion seems to reproduce the seems to produce smaller planets like terrestrial planets rather easily, and it's a bit more difficult to form the larger ones.
Yeah.
Do your predictions fit other predictions or the observations, like with the number distribution of different types of planets?
Of exoplanets.
Yeah.
Yeah, I haven't done that, but it actually there's a review chapter coming out for Protoplanet 7, which Joanna Draskowska is leading, and Miki Lambrechts was a co-author of. And they did a whole thing where they overplotted the exoplanets on top of this, and then they make different boxes and set different percentages, and it looks pretty good, I would say. I think the big question is not always what happens out here. Maybe Jupiter and Saturn are a bit special, because even on solar metal, that many giant planets. So it's also maybe there were a little bit special conditions around the sun. It's clear that a lot of sun-like stars didn't form Jupiter and Saturn, right? So that's why it's really a matter of drawing a box around here and saying 10% or 5% or something. And then
would you be more happy if the Saturn and Jupiter would be right in the center of your models, or is
I don't know.
With you
I think I would like them to be on the outskirts, actually, because we know that the occurrence rate of giant planets is very metallicity sensitive. And you see here a model that's very metallicity sensitive. Just a factor of 2 changes things a lot. And I think once something is very sensitive to a parameter, you're always very sensitive to how you choose it exactly, right? So I think it makes a lot of sense that Jupiter and Saturn for me are the hardest. It's the outermost planets you can possibly form. And you can also, and that's probably also a reason why Uranus and Neptune didn't become gas giants, right? If it was very easy to accrete gas out there and grow fast, they would also become gas giants, yeah.
So for forming gaseous smaller density planets, you need metals.
Yeah.
If metals are involved, how to explain that the planet like Jupiter is of low density? I would expect, sorry, I'm coming from space plasma. How to explain on the one hand side, you need metals, and then you form a planet which is less dense.
Yeah, but you sort of see it maybe here. That if you form Jupiter, it sort of starts out forming its mass, its core, that's maybe 10, 20 Earth masses, yeah. And then from this point on, it only accretes gas. Yeah, so it starts being 100% metals at this point. And at this point is maybe 5% metals or like 10% metals. So from that perspective, you're only accreting gas on top of that. And then, of course, the mystery that people have is that Jupiter's atmosphere is not solar composition. It's enriched in metals by 2 or 3 or 4% or something. So that is maybe a little bit of a mystery, but I think it all makes sense here, right? You accrete solids first and then pure gas afterwards. Then you sort of get this dichotomy.
Yeah, thanks for a very nice talk. So question is are there any systems in which planetesimal accretion dominates the pebble accretion?
Okay.
I don't know, initial conditions or whatnot.
Yeah. Okay. What you can do is that you can make planetesimals even smaller, maybe 500 meters. That's what they do in the Burn model. Modesini and Alibert, they make the planetesimals to be 500 meters in size instead. And then the scale height is very much affected by a gas drag. That becomes very, very thin layer of them, and then they become easier to accrete. The problem I have with that is if you look at the asteroid belt, the characteristic mass size is 100 kilometers. If you look at the Kuiper belt, the characteristic size is 100 kilometers. If you look at planetesimal formation models, the characteristic size is 100 kilometers. So I have an issue with models where you want to fit the data. I mean, models for me is an input parameters and an output parameters, right? And you always want to match the output parameters with the data, but you also have to be careful to not over-select your input parameters, which we all do to a certain degree. But I don't like choosing something that's in direct contrast with observations. And I think going down to 500 meter size planetesimals, I find no evidence of either from theory or from observations. Yeah, so that is the way to go, and then have a lot of them. Yeah, frankly, yeah.
Maybe when I take the last question, I wonder, I mean, your models should also be able to predict the kind of dust to gas ratios as we can observe it. However, that means pebbles are probably very difficult already to observe, but what we see is millimeter particles, and then it becomes quite fuzzy, you know, whether there are centimeter grains in it or not. Going to be difficult. But anyway, if you say, you know, at some point you want to increase the metallicity, which means maybe have more gas than dust, but no, sorry,
more dust.
But then you also say you are running out of pebbles, so that would mean well, the gas should become more numerous than the dust, because you are just taking them away.
You sort of mean you mean in the protoplanetary phase now?
So I'm targeting now possible observations. Would you? I mean, it's very hard actually to measure the gas mass in a distance. It's very difficult. But we are trying to get there. But it would be, of course, interesting whether your model makes some kind of predictions how this dust to gas, the observable dust to gas ratio evolves in time.
It's a very hard problem, because it's very easy. Let's say this was a model of a protoplanetary disk. It's very easy to say you start a pebble here and it's a millimeter in size, and then it drifts into the star in 2 million years. And then you say, yeah, fine, the pebbles are gone after 2 million years. But what if it was 100 micrometers in size? What if it was growing along the way? What if 90% of the pebbles drifted in and 10% stayed out, the sort of smaller ones? And it's actually, it turns out it's actually a very, you know, there's a viscous alpha disk model for the evolution of this. There's no pebble evolution model. So we're sort of working on one now. And I think that the prediction will be that the dust to gas ratio does decrease with time, unless the pebbles are super small. The pebbles are very small, they're just following the gas, because the dust to gas ratio. If the pebbles, even millimeter size pebbles, will the dust to gas ratio should drop with time. That also means some of these disks here. So this is the dust mass. Actually, their gas mass is maybe significantly higher than 100 times more. Maybe they're 1,000 times more even, right?
There's a complication that it seems like when you remove the dust, you also remove the shelter for the gas. So then you'd form winds more easily. So when you take away the opacity, then you would just heat up the gas easier, and then you lose it. So maybe you need some dust to make the gas stay. And so once you take it away, the gas will also.
I think the whole evolution of protoplanetary is still very poorly understood, and particularly also when you include dust drift.
Okay, thank you very much. Let's thank the speaker again.